Everyone. My name is Robert Underwood, and I will be presenting work by myself and my colleagues at Argonne National Laboratory on understanding the effects of modern lossless and lossy compression on the community earth science model. Why lossy compression for climate and weather data? As we know, climate and weather data is huge. No doubt, earlier presentations have already remarked that climate science has enormous volumes of data, easily ranging into multiple terabytes per dataset. To address this, many data compression techniques have been developed. Some of the leading techniques include SZ, ZFP, Imguard, digit rounding, bit grooming, T-thresh, FP-zip, and Z-standard. Each of these methods rely on different compression principles. SZ is what's called a prediction-based compressor, using a combination of regression and Lorenzo prediction in order to predict neighboring values, storing their predictions rather than the underlying values in order to save space. When it is safe. ZFP uses a technique based off near orthogonal transforms, which relates to discrete cosine transform and other related methods used in the past in techniques like JPEG. Imguard is a multinodal compressor that takes advantage of techniques from hierarchical compression. Digit rounding and bit grooming are forms of rounding. T-thresh, however, uses the higher order SVD. FP-zip and Z-standard take advantage of particular patterns in bits. With a variety of techniques available, it's important to be able to compare them. Libpressio is a library that enables this kind of comparison. Libpressio provides over 30 lossless and lossy compression methods, and abstracts between common differences between them. It provides ease-of-use tools such as HDF5 filter support, CLI, R, and Python interfaces. It also has a capability to provide metrics from third-party sources, such as the LDCPY library presented in the previous presentation. Additionally, Libpressio provides opzconfig, which automatically finds settings for lossy compressors which meet specified quality settings. It uses black box nonlinear optimization techniques and works well with any compressor supported by Libpressio. For more information, see our paper in TPDS. What classes of metrics do we consider? We consider mainly lossy compression techniques. Lossy compression has the opportunity to achieve very high compression ratios, and modern lossy compressors allow users to exactly specify what losses are acceptable, allowing users to consider the trade-offs. Relative to prior work, we consider updated versions of SZ and ZFP, as well as 5 compressors not previously evaluated in this context. We also include FP-zip and Z-standard for comparison. The first question to answer in lossy compression is how similar is good enough? We also use metrics from the work by Pignard and L. In practice, their DSSI metric as well as the KS test metric are the binding ones. Also, unlike prior work, we consider all 4 major models within the CESM framework. Atmosphere rightly has observed most of the interest up until this point. This is because of its truly massive data volume. However, the other 3 major components also produce large datasets, which may benefit from compression. Which compressors do the best? As always, it depends. Right now, lossy compressors SZ and ZFP tend to do better on the atmosphere and ocean datasets. You can hear more about how SZ3 accomplishes these performance results in the next presentation. Whereas specialized encoding methods such as FP-zip did best on land and ice. The latter are relatively small per buffer, and the associated metadata and entropy costs required for this generation of compressors tend to exceed the benefits. However, 2 techniques may improve this for future work. First is a feature from the Z-standard compressor, known as Common Dictionary and External Metadata. These 2 features externalize the 2 forms of overhead so that they can be shared between invocations of the compressor. Fully leveraging this, however, would require changes to netcdf and HDF5. Additionally, larger trunk sizes may also improve the competitiveness of lossy compression. So what compressors are bottlenecked by which metrics? For SZ, the KS test tends to be the limiting factor. In order to pass this case, it needs a value range relative air bound which is smaller than 1 × 10 to the -15th. With this highly restrictive air bound, SZ does not improve much over lossless compression. However, for the three other metrics, SZ is able to achieve high compression ratios greater than 30. For ZFP, the other compressor that performs well, it has an easier time of meeting the quality requirements, but achieves a much smaller compression ratio, barely larger than that of lossless compression. For context, the best lossless compressor achieved a compression ratio of 2.2. Other lossy compression techniques that exist either get a worse compression ratio or perform worse on these tests. If you have any questions, please feel free to reach out to me at runderwood@anl.gov.